there is this very famous Beer-Lambert law that you will basically apply and use in whatever you do as a bioscientist. So that's in the first session. And in the second session, I quickly will whiz through the comprehension question from the practical, because people have asked me if I could go through that. So I will be happily of service if people had problems with that. There are no, there's no register today, so it's entirely up to you whether you want to be here or not. That's, your choice. Okay, with this spectrophotometry, you have already done an experiment with that, where you were able to measure concentration of a substance just simply using light. So that's the topic today, spectrophotometry. And for most of the uses that, or the applications that we use in biosciences, we will use the electromagnetic spectrum, part of the electromagnetic spectrum, and probably in most cases we will look at the electromagnetic spectrum in this range here. So this includes visible light, which is from about a wavelength of 400 nanometers to about 800 nanometers. There is also something called infrared spectroscopy and also UV spectroscopy. And you have used a little bit of UV spectroscopy already when you measured the concentration of this protein solution of BSA. And why this works, I will come back to you in a minute. So how do these things actually work? What's happening? What's going on there? Okay, so basically what we are looking at is the interaction of electromagnetic waves with matter. So in a way, we have an electromagnetic wave, and I'll symbolize that with this waveform, and it hits some material. And we use that. Because what happens is that very often, through this interaction, the electromagnetic wave, something happens to it, something happens to the matter, so sort of a collision, if you like. And when we send this electromagnetic wave onto something, and we measure what comes out at the back, we find that less of the wave comes out. Or, in other words, some of the electromagnetic wave is absorbed. Why? What's happening here? Why would we absorb electromagnetic waves? Well, the answer is, in a way, trivial and not trivial. In a way, electromagnetic waves, like light, but also like any other wave form, are just simply forms of energy. And in this case, we shoot energy, and energy then is absorbed. That's a very simple explanation. A little bit more in-depth explanation is that we need to have exactly the right amount of energy to do something. Why is that? Simply because this energy that we are using interacts, basically, the energy interacts predominantly with the electrons in the material. And we know that electrons are moving on in particular orbitals. Yes? I know that you love that. Orbitals in chemistry. You heard about them? These electrons are sitting in particular orbitals. They are not just, randomly floating around. They are in particular levels, energy levels. And what happens actually then is, why don't we do a little experiment? Can I borrow you for a moment, please? Okay, so I'm an electron. You look very energetic today. Yeah, so you are a wave. Yeah, and I'm just floating around somewhere. My nucleus. Yeah. You are my nucleus. Yeah, high nucleus. And now a wave with energy comes. Push me. Yeah. Oh, just lousy energy. Yeah. Push me a bit harder. Oh! Oh my God! That was a lot of energy. Well, my nucleus. Yeah, I lost my nucleus. I got actually pushed out from my beautiful nucleus. Where is he? So if too much energy is there, I float away. Okay, now let's try that again. Just push me a little bit. It's exactly the right amount of energy to make me jump to the next level in my orbital. Too much energy, it sends me flying. Not enough energy, I will totally ignore it. I'm now on my next level of of energy, and it's quite comfortable here. Although this is sort of, there's a gap down here, an energetic gap. So in a way, what I'm going to do is jump down again. Push again. And it's again the right energy, and I jump up to my level. Thank you very much for the wave. Thank you. Big applause, round of applause. So when we have this interaction between electrons and energy, we need to have exactly the right amount of energy so that the electrons are able to jump to the next level. They absorb this energy and sit on a higher level. When they are up there, actually, and they are then up there on their high energy level. And we take away the energy. What they do then very often is they just simply fall down on the next lower energy level. Energy is released, and all of a sudden we see this energy as well. But that's a different story. This energy that is then released when the electrons fall down again after the push is called fluorescence. So when we talk about fluorescence, this is what happens. We excite the electrons in the first place and then let them fall down again. Now, was it hard work? Was it hard work? Yeah, it was hard work. Extremely hard work. Sorry, what's your name?
Chris.
Chris. So Chris is absolutely shattered now from pushing me. And this is because I absorbed the energy. Yeah? So this is basically how light, how electromagnetic waves interact with matter. You had a compound in the practical, paranitrophenol, and this compound is characterized by a number of electrons that are sort of in a state that is easily pushable, easily excitable. So we can use light that doesn't have too much energy. It has exactly the right amount of energy to bring the electrons to the next level. In BSA, the electrons are more difficult to excite. They are tighter bound around the nucleus. So we need light with more energy. That's why you used ultraviolet light, which has more energy than the light that you used for the paranitrophenol. So the big thing is you always have to use the right light if you want an interaction between energy and matter. And this light is dependent on each substance. So the light, if I call it like that, it can be other electromagnetic energy. Light depends on the interaction with the substance, or it depends on the substance. And usually we measure the light in wavelength that is usually in nanometers. So you did the experiment with the paranitrophenol at a wavelength of 405 nanometers around here. So that is bluish purplish light. And it has a certain energy, very distinct characteristic energy. And only at this wavelength, the electrons of the paranitrophenol are excitable. Okay? That makes sense? Yeah, it's pretty simple. Okay, so let's say we have a substance in here. Oh, let's do red dots. 2, 4, 6, 7. 7 dots. And we shine light onto this substance. Obviously, our container should be clear. It should not absorb the light, because that's pretty pointless then. And let's say our red dots will absorb the light. Not all of the light. Some of the light will go through. So let's say what we see is 2 of the light goes through, so 50% of the light goes through. Okay? What would happen if we add another container? With the same substance? What do you reckon? Sorry? Nothing comes through. Ah, that's interesting. I like your thinking. I really like your thinking. We said here 50% of the light goes through. Yeah? So if we shine a little bit less light, then it's probably that, again, 50% goes through. Yeah? So maybe only 1 goes through. And that is actually what happens. So the amount of light that goes through depends on how many containers I have, basically. Or actually, not necessarily 2 separate containers, but it could be that I have the scenario of this one would be exactly the same as me having a container like that, twice as thick, the container. Yeah? Make sense? So what we can write in the first place is our absorbance, how much of the light is getting absorbed, depends on the thickness of our container. How big is this container? We abbreviate that with D. This is the thickness of the container, and very often it is, or usually it is 1 centimeter. That is the path length. Some people call it path length. Of the cuvette. Okay? Does it make sense? The thicker the container, the bigger the container, the longer the light has to go through this substance, and the more is absorbed. This symbol here simply means it is positive correlated. It is directly dependent on the thickness of the path, on the path length. Okay, here's another question for you. Here we have our substance in the cuvette. These dots, the substance absorbs the light. And let's say we get 2 out. So we get 50% out. as we had before. Yeah? Let's do the same thing. I have now doubled the amount of dots in the same volume. Remember, amount per volume is concentration, exactly. So I've doubled my concentration. What would you expect to happen to the amount of light? How many of these light bits should I draw? One? Excellent. Why one?
25%.
Exactly. So all but one gets absorbed. So the absorbance, in this case here, is not just dependent on the length of the path, but it also depends on the concentration of the substance. So depends on the path length, and absorbance depends on the concentration of the substance. The more substance that absorbs, the higher the absorbance. Right, so all we need to do is now put these things together, and we have a little equation that we can readily use. And for that is, in order to put things into an equation, we can write absorbance equals the concentration, and very often people just simply abbreviate that with a C for concentration, although in this case it's very, very dangerous because it could be the speed of light. But usually we don't manipulate the speed of light. When we do that in terms of biosciences, we know that this actually means concentration. Concentration times the path length times a factor that makes this sort of into an equation. And in our case, we call this factor epsilon. It's the Greek epsilon, which stands for extinction coefficient. So that's the extinction coefficient, and this extinction coefficient is dependent on the substance, it's dependent on the environment of the substance, and it depends on the wavelength of the light or the energy that we're using. So extinction coefficient depends on substance, environment of substance, and the wavelength. Okay? And what we have here is actually an extremely useful equation. Absorbance equals concentration times length of the path times extinction coefficient. This equation here, this is called the Beer-Lambert law. And this is going to stay with you for the rest of your degree. So you better learn it now. It's not terribly challenging, I'd say. What this actually allows us is we can measure concentrations of substances just by simply measuring how much light is absorbed by this substance. As long as we know D and the extinction coefficient, we can easily measure how much of a substance we have. Like you did in the practical, where you whacked your sample into the spec and you measured how much absorbance do we get from that. And that tells you what the concentration is. We need to, one more thing that we need to be aware of, and that is sort of that reflects my nickname. People in previous years have called me Mr. Unit because the rumor is that I have a fetish about units. No, it's nothing kinky. And we need to talk about units. And so, the unit for absorbance, unit, there is no unit for that. Absorbance does not have a unit. What makes it easy? The path length, that usually has the unit of centimeter. And the concentration, what unit is that? Molar? Yep, that's right, that's molar. Or mole per liter. What is epsilon? Ah, that's difficult now, huh? Let's see if we can figure that out. A very simple way of figuring that out is we just simply write our equation in terms of units. So abs equals C times D times epsilon. Abs has no unit, equals molar times centimeter times. So we need to basically, if we want no unit on this side here, what we need to do is that with this one here, it should cancel out all the other units. The easiest way to write that is molar to the power of -1 times centimeter to the power of -1. Because what happens with the units then? They cancel each other out. Make sense? Yeah? Actually, when you use this trick, and we will use that then later on in later lectures shortly before Christmas, you can actually find out the unit of basically anything. You just write what is called a unit equation. So what we can say now is the unit for our epsilon is molar to the -1, centimeter to the -1, which is the same as liter per mole and centimeter. So some people write it that way. Some people write it with exponents to the power of -1. But both things are exactly the same. Are you happy with that? Yeah? Now, how do we get these epsilon? How do we find these epsilons? Well, lots of people have done experiments for certain substances, and these extinction coefficients are actually published. But we can also figure out epsilon ourselves by doing some experiments. And what we do is we use a known substance, or a substance with a known concentration. Like that, known concentration, in a known path length, say 1 centimeter. We whack that into our spec. And then we step by step change the wavelength. Change wavelength. What do we get? We measure our absorbance, and here is the wavelength in nanometers. And what we will see for many substances is that there is one particular wavelength where this substance actually absorbs. This here would be maximum absorbance. At this particular wavelength here. So I found the optimum absorbance, the optimum wavelength under which I have to do my experiments. And just simply knowing the absorbance, knowing the concentration, knowing the path length, I just simply rearrange my Beer-Lambert law. Absorbance equals C times D times epsilon. Epsilon equals absorbance divided by C times D. And I get my extinction coefficient. Simples. By the way, such a spectrum is called an absorption spectrum. Because we go through the entire spectrum of the wavelengths that our spec is capable. Make sense? So, oh yeah, just to confuse you a little bit. Because that was so simple. When we have a substance, okay, let's go for a nice substance. I don't know whether you see that. I think this should be red. Let's say this is red. We see it as red. Was that Netflix? Okay. I'm very glad that it wasn't... you heard about that story of the guy who was in a law lecture who was watching porn. And unfortunately, the headphone came out of the headphone jack. And so the entire, area had the pleasure of, literally had the pleasure of being involved with that until somebody pointed it out to them. And the poor sod had to leave and never ever was seen again in a lecture. So if you do watch things, make sure that your headphones are plugged in. Anyway, we have something that appears red. Why is it red? Why is something red? Hey, why? It depends on the wavelength, exactly. Why are leaves green? Because of the chloroplasts, yeah, physically? Or in terms of physics, why are leaves green? It reflects, loud, say it out. Absolutely right. If you've got green leaves, because of the pigment in the chloroplast, light is absorbed. Specific light is absorbed. While other light is not touched, and this other light is basically reflected, and that is what we see. Can you figure out what is the wavelength of the light in the chloroplasts that is absorbed? What is the light that is absorbed by the chloroplasts? Loud?
Around 700 to 400.
Around 700 to 400. Well, everything is absorbed.
Around 700 and then around 400.
Around 700 and around 400. So we absorb basically in this range in the chloroplasts, and we are absorb in this range in the chloroplasts. We don't, if you are a leaf, I mean, chloroplasts don't absorb very well in this range here. And that is why you see leaves green. This is from the different photosystems, photosystem 1 and photosystem 2, that absorb this specific light. Why do you actually see leaves in autumn turning red? Why do they turn red?
The magnesium is removed from the leaves.
Sorry, they make?
Magnesium is removed from the leaves.
Magnesium is removed from the leaves. That's a very... But why do they turn red?
Because the magnesium is the thing that reflects green light.
Nope. Magnesium, you are on the right track, actually. Yeah? In autumn, chlorophyll is destroyed. And in a way, it is recycled by the plant. It's a very important thing because it contains a lot of carbon and it contains lots of nitrogen. chlorophyll. So it would be a total waste throwing that away. So what the plant does in the first step is it removes the magnesium, that's the central ion in chlorophyll, and that triggers the breakdown of chlorophyll. So the chlorophyll that absorbs in this range here disappears. The plant does not look green any longer. And in fact, this wavelength here in this range, there is some absorbance by other pigments in the plant. But usually it's totally masked by chlorophyll. But what happens in this case is that now there is good absorbance still in, or there is some absorbance still in this range here, and no longer absorbance in the red light area, and that is why leaves in autumn turn red. So you learned something. Does that make sense to you guys? Fantastic. So, any questions? You should now be able to do this spectrophotometry quiz. That's on your quiz list. Give it a go, see how much you can do with that. Okay? We have a 5-minute comfort break, and then I will go through the model answers. Okay?